At the same time, the torque generated by the propulsion bar is transmitted to the steering wheel, giving the driver feedback, informing him of the steering reaction. In summary then, the control valve generates appropriate assistance by changing the direction of the flow of power steering fluid and by controlling the flow volume of the fluid. So far, the basic construction and function of the power steering system has been explained. In a real automobile, however, various other mechanisms are added to improve steering. Steering effort varies with vehicle speed, and the required steering effort is less at higher speed. From the driver's standpoint, the ideal would be for the steering system to change in accordance with the vehicle speed. For example, when the driver has to turn the vehicle sharply at a low speed as we start the car, the vehicle should be able to be steered with the steering effort. On the other hand, during high-speed driving, the steering wheel should be firm, yet responsive. In order to attain this goal, various systems are utilized so that the assistance will be provided in response to vehicle speed. Let's take a look at two typical systems: engine speed sensing power steering and vehicle speed sensing power steering. This graph was used during the explanation of the vane pump. It shows the relation between engine RPM and the flow volume of the power steering fluid. In engine speed sensing power steering, the engine RPM increases, the flow volume of the fluid generated by the vane pump decreases, as shown in the graph. For this reason, the required steering effort is increased by reducing the assistance. Now let's take a look at the mechanism that reduces the flow volume. In engine speed sensing power steering, a control spool is added to the flow valve of the vane pump. This is a control spool. Located between the control valve and the orifice, the control spool reduces the flow volume of the power steering fluid by closing off part of the orifice. When engine RPM is low, the hydraulic pressure from chamber A is applied to the control spool. Although this should be enough to move the control spool to the right, the spool cannot because spring tension is too great, so the flow volume of the fluid does not decrease. This corresponds to the point shown here on this graph, which we saw earlier. As the engine speed increases, the hydraulic pressure in chamber A increases, so the control spool overcomes the tension of the spring and begins to move to the right. The pressure in chambers B and C decreases because the orifice is gradually closed. This creates a large difference in pressure between chamber A and chamber C. The flow control valve moves to the left due to the system, and a lot of fluid is discharged, causing the flow volume of the fluid to the power cylinder to decrease. As the engine speed further increases, the control spool closes off more of the orifice. But even if the engine speed is further increased, and the hydraulic pressure in chamber A also goes up, the flow volume of the fluid to the power cylinder is kept constant because a lot of fluid is discharged to the suction side of the vane pump. This corresponds to this point on the graph. This is how engine speed sensing power steering reduces the assistance given when engine RPM is high. This produces an agreeable steering feel by providing appropriate steering wheel response even during high-speed driving. In vehicle speed sensing power steering, based on signals received from the vehicle speed sensor, the ECU controls the current of the solenoid valve and the steering gearbox in accordance with the vehicle's speed, thus controlling the steering effort. Now let's discuss one type of vehicle speed sensing power steering, the hydraulic reaction progressive type. The features of the hydraulic reaction progressive power steering system are as follows. A hydraulic reaction chamber is provided inside the control valve housing, and as the vehicle speed increases, hydraulic pressure makes the torsion bar more difficult to twist, with the result that the steering wheel becomes heavier. In this way, a torsion bar that is thinner than in an ordinary power steering system is used to reduce steering effort during low-speed driving. In the construction of a hydraulic reaction progressive power steering system, a solenoid valve, a flow dividing valve, and an orifice have been added to the previous power steering mechanism. As current from the ECU increases at low vehicle speeds, the opening of the solenoid valve also increases, decreasing the pressure in the hydraulic reaction chamber. The flow dividing valve channels the fluid from the vane plug to the hydraulic reaction chamber. This is the construction of the hydraulic reaction chamber inside the control valve housing. When the pressure in the chamber increases at higher speeds, the plunger uses that pressure to push the control valve shaft in opposite direction from that in which the steering wheel was turned. This increases the steering effort. Now, let's see how hydraulic reaction progressive power steering operates. A passage leads to the hydraulic reaction chamber through the flow dividing valve, and a special circuit controls the flow of the fluid by means of the solenoid valve, which is located midway in the passage, leading from the pump to the power cylinder. Since the solenoid valve is wide open at low vehicle speeds, the fluid that goes through the flow dividing valve returns directly to the reservoir via the solenoid valve without passing through the hydraulic reaction chamber. This allows the steering wheel to